for attending the webinar today. It's called Optimize Your Polymer Analysis by Selecting the Ideal GPC-SEC Column. So to start, I always think it's always important to provide a quick reminder for the GPC-SEC separation mechanism. How actually does GPC-SEC work? So quickly, the GPC-SEC column is packed with porous beads of controlled porosity and particle size. Your sample is prepared as a dilute solution in the eluent and then injected onto the system. The large molecules are not able to permeate all the pores and have a short residence time in the column. The smaller molecules will permeate deep into the porous matrix and have a long residence time in the column. The sample molecules are separated according to molecular size, eluting largest first and smallest last. Remember, first and foremost, GPC is a non-interactive technique. It's a technique that will separate your polymer samples based on their size and solution and not on their chemistry. As it is a non-interactive technique, no interaction of the sample with the column packing is wanted. So why is SEC and GPC used for polymer samples? It's run to determine the molecular weight information and averages and the molecular weight distribution information for polymer samples. Knowing this type of information about your polymer can be critical to its use. Here briefly, we describe a typical GPC workflow, and this would be for conventional GPC. Your steps would include to calibrate the GPC-SEC column with a set of well-characterized polymer standards. You'd then plot the retention time of these standards versus the peak log molecular weight value, creating the calibration for your column set. An example calibration is shown here on the left, looking at the standard chromatograms in red and blue, and then the calibration plot showing each of those molecular weight standards. Next, the calibration is used to generate the molecular weight averages and distributions of your unknowns run on the same system and column set. In blue here is an example of a sample chromatogram detailing the slice information and then the differential log plot showing the distribution and the molecular weight averages for the polymer sample. The molecular weight results of the unknown samples will be relative to the polymer standards used for the column calibration. If absolute molecular weights are required, one would consider using multi-detector GPC. So when we need to select a GPC or SEC column for our samples, what are the steps that we need to take when we're looking to select our column? There are a number of key questions we should ask. What polymer are you analyzing? Which solvent or solvents is your polymer soluble in? What is the expected molecular weight range of your polymer? And what's the requirement for the analysis, or what would you like to improve on for your existing GPC-SEC application? Is resolution important? Reproducibility of the sample, chromatography and results? Is the speed of analysis or sample throughput something you'd like to improve on? Some further considerations: it's important to know the properties of the sample and be familiar with the properties of the columns that are being considered. And it is also important to balance polarities of the sample, solvent, and the column packing. There are many choices for packings for GPC and SEC columns. One tends to find that the columns are typically of two category types: polymer chemistries or silica chemistries. For polymer chemistries, the polymer chemistries have higher pore volume, and pore volume is important for the size separation. Between vendors, you can see that there are many differences in mechanical stabilities for packing, so it's always good to check their technical specifications. We will see that polarity of the stationary phase is important in choosing one with a polarity that is similar to your sample and solvent. Observed interactions will be reduced. In a lot of today's commercial polymeric GPC packings, you can find them being made of such polymers as polymethacrylates, polyester copolymers, DVB divinylbenzene, or polystyrene divinylbenzene. With the silica chemistries, they typically have a lower pore volume versus the polymeric, but they are mechanically stronger. They exhibit enthalpic properties due to the presence of the silanols. Some common silica packing types are diol, surface-modified hydroxyl, or surface-modified polymeric. Agilent has two excellent tools to use when someone's looking to see what column family might be considered for their samples. This is called the magic triangle. We have one for organic soluble polymers and one for aqueous. Here's the example for the organic soluble polymers. Here we show an equilateral triangle indicating balanced polarities, which is a requirement for obtaining a true molecular size only base separation. You need a balance between sample polarity, mobile phase polarity, and packing polarity. This is critical for running GPC as no interaction of the sample and the packing is wanted. Look at the outside of the triangle. Say our sample is polystyrene, seen here in the lower polarity range. Looking at this inside red triangle, a common solvent for polystyrene is THF, which we see also here is in the lower polarity range for our solvents. If completing our triangle, we can see that the PL gel or the STV column families would be our recommended product for this sampling conditions. If our sample was PMMA, more in the medium polarity range, looking now at the green triangle, using a more polar solvent like DMAC in completing our triangle, we see that the gram, the polar gel, or possibly the polar shell columns could be the column family to consider. As you can see, no single column packing is suitable for all analytes. If working with water-soluble polymers and aqueous mobile phase conditions, we have this triangle for water-soluble polymers to help with selecting an appropriate stationary phase. For water-soluble polymers, where the main solvent is water, you need to consider the ionic character of your sample. And secondly, pH will be used for this type of sample as well. If we look at the outside triangle, let's look at neutral macromolecules. Inside the bigger triangle, look at the blue inner triangle. With these sample types, these would be run at a neutral pH 7. If then looking at the third point of the triangle, we find that the Suprema or the PL Aquagel OH stationary phases are those best suited for these types of samples. If looking at something like polycations with the light green triangle, these sample types are recommended to run at low pH, and if finding the third point of this triangle, we see that the Novema Max stationary phase is best suited for these sample types. Both of these triangles can be what you can first use, and they can be a very helpful tool when starting to look at your GPC SEC column selection. Within the column families, we find many options for columns available, and there are characteristics for these columns that we need to look at. First might be column porosity. Column porosity, or the column pore size, will determine the size separation range and hence the molar mass separation range for your column. On this slide, we'll be depicting two common types, individual or single pore sizes, and linear and mixed pore sizes. Example calibration shown here in these plots. For the individual pore size columns shown in the blue calibration plots, these will exhibit a calibration curve with a shallower gradient indicating higher resolution within a specific molecular weight range. For example, compare the 100 angstrom pore calibration curve to the 10,000 angstrom curve. The molecular weight ranges for these columns are more specific. Combining columns of different pore sizes will extend the separation range, and if combining columns of the same pore size, this will increase resolution. For the linear or the mixed columns, depicted here by the orange curve, these are a later or newer development of columns. These have a blend of different pore sizes in one column with a fixed analysis range. It's recommended to use columns of the same type together, and combining columns of exactly the same type of linear or mixed bed will increase resolution. Another type of packing porosity is the multiporous particle. This is the newest type of particle, and as it describes, the particle is made to be multiporous. The particle itself will have pores of different sizes on it. A benefit of having this is an increase in pore volume available for the separation. These particles provide for highest efficiency and resolution, and for best performance, these are provided for the most common molecular weight ranges of Agilent's organic GPC columns. Here on the right, we have the calibration plots for the Agilent Plus Pore family of columns. Like with the linear or the mixed columns, if working with columns from the Plus Pore family, it is always recommended that they be run together in series with columns of the same type. So when might you choose each type of column? Here we have a side-by-side comparison for the different porosities. The top is a bit of a review for the last couple slides just discussed. When might you choose to use an individual pore column? You might have a very specific molecular weight range for your sample. These individual pore columns allow for flexibility where you may want to be able to add or remove a column based on your needs. For very high molecular weight samples or for viscous solvents, use of large particle individual pore columns can help with issues that might be related to shearing or viscous fingering. You may find these types of columns most often used in R&D settings or for older, well-established methods. For the linear and mixed columns, these can be great first-use columns to screen your sample. A single column can be used for this scouting purpose. These columns can also be used when looking to replace an individual pore set for reducing runtime when analysis time and throughput are important and without sacrificing resolution. The linear mixed columns are often used for routine analysis like in a QC setting where molecular weight ranges for the samples are well defined. In the last couple slides, we've been talking about the packing porosity and noting pore volume. Here we have an example to show a comparison for two column types, a PL gel individual pore 5 micron column and the multiporous packing type oligopore column. Both of these columns are very specific for low molecular weight GPC separations. This is a great slide to show the benefit of having more pore volume. For each column, we're using a 2-column set. And our graph is showing the calibration plots for each of the 2 columns. Both columns have a similar exclusion limit, but the oligopore has greater pore volume than the PL gel 100 angstrom. Because of this, the slope of the curve is shallower, leading to greater resolutions for columns of similar efficiencies. When looking for columns, one might find that there are usually many particle size offerings. The typical range of particles is usually between 3 micron and 20 micron. With smaller particles, one would expect improved resolution and efficiency for the same column length or faster separation with similar resolution. Here in our example, we have 2 individual pore SDV 1000 angstrom pore size columns, a 5 micron and a 3 micron particle column. Here we're showing the same polystyrene standard sample run on the 2 columns, each of the same length. As you can see, with the smaller 3 micron particle packing, one sees improved resolution for the 4 standard peaks, improved peak shape, and for the lowest molecular weight standard, much improved resolution for the polystyrene oligomers is seen. If someone was looking for a GPC separations for very low molecular weight compounds such as mono, ditriglycerides, or even linear hydrocarbons, a small porosity, small particle column is generally recommended, like that of the 3 micron 100 PL gel or the oligopore column. A question that is sometimes asked is what are the limits when using smaller particle sizes? Certainly there are times when this could be an issue. Large molecular weight samples, for example, like polyolefins, the problem with using a small particle for these very large molecules would be that you could deform or possibly shear the molecule, causing degradation or breakdown. To avoid this, a large particle packing is recommended. Look at the example chromatogram here on the right. We show a 10 million polystyrene standard and it being run on 3 different particle size columns, 10 micron, 5 micron, and 3 micron particles. As you can see, the polystyrene standard run on the 3 micron particle, we have a completely distorted peak. The 5 micron particle is also showing some shouldering and some peak shape issues. With the 10 micron packing, the peak shape for the standard looks as we might expect. For these larger molecular weight samples, it also might be suggested to work at lower flow rate. In the graph on the left, with increasing flow rate, note as the molecular weight increases, the plate height increases rapidly and therefore the plate count decreases rapidly. Large molecules will require lower flow rates. Another consideration is related to the solvent that may be being used. For viscous solvents, small particles will incur higher operating back pressures, and working with larger particles will aid here, helping to reduce the overall back pressure. Unlike other forms of LC, GPC and SEC typically use more than 1 columns in series. As the separation is one that is non-interactive, it relies on the sample's ability to permeate in and out of the pores of the column packing. The more pore volume for the sample, the more resolution that would be expected. So typically, what is the number of recommended columns to use? The number of columns recommended is dependent upon the particle size of the GPC packing. And you can see the table here with some recommended numbers of columns per particle size. The larger particle columns are needed for higher molecular weight samples, and the number of columns in series is higher as these columns will have lower efficiencies. More columns in series is used to increase resolution for the high molecular weight samples. For example, a 20 micron column, typically 4 columns in series is suggested. For lower molecular weight samples, smaller particle size columns can be used as shear degradation is not a problem. With the smaller particles, the column's efficiency will be increased, so less columns in series are required to give good resolution. One does need to remember that with the addition of columns in series, this does help to improve resolution, but it does also mean that your runtime will be longer. In the earlier slides that depicted the 2 triangles, which we can use to help us select our column product family, here in these next couple slides, we'll delve a bit deeper to discuss the various column packing families. First here we have our columns typically used for low polarity eluents, our PL gel, the plus pore, and the STV column families. Our packings are polystyrene or styrene divinyl benzene, and it's one very similar in polarity and will be well matched for use in these types of solvents. The typical solvents used here might be something like THF, toluene, chloroform, as well as something like ethyl acetate or 2-methyl-THF. These columns are very suitable for sample types such as polystyrene, polybutadiene, polymethyl methacrylate, silicones, epoxy resins, for example. If we look at the table here, we see that the various column particle sizes are available in various pore sizes and column size options that are available for each. The PL gel offers a premium product with our mixed columns optimized for most often used molecular weight ranges. Available also in individual pore columns from sizes small ID 4.6 all the way up to preparative sizes 25 millimeter columns are offered. The plus pore family is a newer packing family featuring columns with the multiporous particle that offer more pore volume for improved resolution. Again, numerous column sizes are offered. In the plus pore family, the oligopore is also offered in a prep size, and we do offer these columns in standard column sizes as well as smaller 2.1 millimeter ID if someone may be interested in mass spec work. The styrene divinyl benzene product family also offers packings of different particle and pore sizes available in linear and individual pore packings covering a wide molecular weight range. Where there is an asterisk, for example with PL gel and STV, there are select columns that are recommended if wanted to use with light scattering detectors. These columns are made to minimize startup time for use with light scattering detectors. Just a quick example for a polyester sample run on a ResiPore column. The ResiPore is from the plus pore family and it is a 3 micron multiporous particle type column. It has a molecular weight range up to 25 K and is good for running low to medium molecular weight samples. Our example here is using 2 columns in series running THF. As you can see, we have a nice peak here for our sample, but what's even better is that with running with this sample on the 3 micron high efficiency particle column, we can easily see the oligomeric detail for this sample. Next, let's look at our column families if working in medium polarity eluents. The product families would be Gram, Polar Gel, and Polar Sil. These packings have polarities and characteristics that are well matched for working in medium polarity eluents such as DMF, DMAC, and MP, for example. These columns are well suited for running some samples such as polyurethanes, polyamides, cellulose starches, amylose, amylopectin, as well as others. Here again, we show a table for the gram, polygel, and polishil columns. The gram is a polyester copolymer packing. It has columns of both linear and individual pore types. These can be used for very high molecular weight samples such as starches. So is offered in a larger 10-micron packing, which is good for working with these higher molecular weight samples and also good for working in viscous solvents. The polygel columns. The polygel is a mixed bed column. It has a medium polarity surface and high mechanical stability. These are offered in an 8-micron particle size and in 2 molecular weight ranges. These are good columns for the analysis of medium molecular weight polymers such as resins and lignins. The polishil is a packing with a polar modified silica packing. It's offered in both linear and 3-micron individual pore columns, molecular weight ranges, 3 individual pore columns. It's offered in molecular weight ranges up to 1 million, available in both a 5 and a 3-micron particle size. These columns can be good for running low molecular weight mass polymers where oligomeric details are of importance. These two are also offered, available for use with light scattering detectors. Here we have an example separation showing hydroxypropylcellulose, which is a derivative of cellulose with both water and organic solubility. It is used in a number of different applications, such as being an excipient, a thickening agent, and a binder. It's also used in ophthalmic products. The degree of substitution of the glucose ring of the cellulose with hydroxypropyl groups affects the solubility in water. As an alternative, it's possible to analyze these samples in an organic solvent such as DMSO to avoid these solubility issues that you might have with water. Here we have a gram GPC column, 10 micron linear, which is a good column as these polymers are very polydispersed. We're running DMSO with lithium bromide salt and running at an elevated temperature of 60 degrees with RI detection. As you can see from our example chromatogram and distribution plots, for our two samples, we see they are indeed of different molecular weights. With using conventional polymethyl methacrylate calibration, this would enable calculation of the molecular weight distribution as well as average molar mass values. The values that would be calculated for the two polymer samples will be relative to the standards used. What if your column need is for high temperature GPC application? This is a very specific application area running special GPC SEC systems and special columns for temperature conditions and solvents that are needed. Our product families here would be PL Gel Alexis, PL Gel, and Polifin columns. The typical solvents used in these high temperature applications tend to be TCB, ODCB, chlornaphthalene, butylol, for example. Typical samples that are running using high temperature GPC are polyolefins, polyethylene, polypropylene, and many high performance polymers. The PL Gel Alexis columns are optimized for the analysis of polyolefins and these high performance polymers. Its 13 micron particle packing is highly porous, offering high stability and high pore volume for resolution. The 13 micron particle with its 10 micron column frit is important for no shear degradation for these high molecular weight polymers. And these columns provide for extended lifetime at these very high temperatures. The PL Gel family offers a couple of specific mixed bed columns for these analyses. The mixed A 20 micron and mixed B 10 micron packing respectively. The mixed A is well suited for ultra high molecular weight polymers, with the mixed B ranging up to about 10 million. And the polifin packing as well is good for these polymers, offering two linear type columns, a medium molecular weight and large molecular weight, 10 and 20 micron particle packings. There is also 10 micron individual pore columns available. These columns too, for the mixed A and the mixed Bs, these columns are available as LS columns and for use with light scattering detectors. Polyolefins can range from low molecular weight hydrocarbon waxes to ultra-high molecular weight rigid plastics. GPC is an important technique used for characterizing these polymers. The molecular weight distributions of polyolefins is directly related to the physical properties of the polymer, such as toughness, melt viscosity and crystallinity. High molecular weight polyolefins tend to exhibit very broad molecular weight distributions. For such samples, small particles with small pores are not recommended as shear degradation would occur, so the 13-micron large particle, wide molecular weight range PL gel Alexis column is well suited. Here we're showing a series running various molecular weight polyolefin samples. Our example shows the differential log plots for our various polyolefin samples, clearly showing that the molecular weight range for the Alexis column can cover the various molecular weight differences and distribution for all our polymer samples. There are some very specific application-specific columns also available. Example for those polymers requiring fluorinated solvents. These two product families, their packings are well matched for the analysis of these types of polymers. Polymer samples tend to be very high in crystallinity and require these fluorinated solvents for dissolution. Typical solvents used are HFIP or TFP and other fluorinated solvents. A couple examples of these sample types are listed here: recyclates, polyesters, PET, polyamides, for example. PFG is a polar-modified silica. It has a wide range of column types. Linear and individual pore columns are available with 5-micron or 7-micron particle sizes. This packing provides for both robustness and for resolution. Small pore and small particle 5-micron columns provide for high resolution and separation of oligomers. The HFIP gel is a 9-micron multiporous particle packing, offering for an optimized separation range and delivers high performance with no mismatch artifacts. Both columns are offered in standard IDs and lengths and also available in smaller 4.6 millimeter ID dimensions, as with these applications, running for reduced solvent consumption is often desired. These two are also available as LS columns for use with light scattering detectors. Here's a quick example showing GPC of polyethylene terephthalate. Here we're showing the HFIP gel columns being used. In this example, just a single column in HFIP with salt is being running at 40 C at 1 mil per minute, and the system is calibrated with PMMA standards, as these will give expected size behavior in HFIP. The application can be run using conventional Agilent HPLC modules, or for flexibility and safety, often a high-temp GPC system may be recommended. As you can see from our chromatograms, we have nice overlay data for our various PET samples that were analyzed. For running in aqueous eluents, the next couple slides details Agilent's SEC column product families. Here are the columns for running neutral or weak anionic type water-soluble polymers, Suprema and PL Gel Aquagel. These packings are well suited for the analysis of such polymers as synthetic polymers, some of those used in cosmetics and food ingredients, hyaluronic acid, polysaccharides, dextrans, for example. The Suprema columns offer the widest range of SEC columns for particle size, pore sizes, available in linear and individual pore size packings. This column is specifically suited for a number of USP monographs noted here. Columns can work in a pH range of 2 to 12, and these columns are compatible with organic modifiers up to 100%, making this a very versatile and robust packing material. Suprema is offered in high resolution, high efficiency 3-micron particles as well. PL Aquagel is a neutral hydrophilic packing and can work in mobile phase conditions pH range 2 to 10. It is suitable for some cationic polymers. It can be used with methanol up to 50%. Aquagel is also available in a larger 15-micron particle size for the analysis of very high molecular weight polymers. The Suprema columns, there are some select columns available here too for use with light scattering detectors. Here we show an example showing the use of some Suprema SEC columns. This analysis is of a dextran sample, molecular weight 1260 Daltons, on Suprema low molecular weight combination of 3 Suprema 5 micron 100 angstrom columns. The separation shows the increase in resolution seen when using the high efficiency 5 micron particle and when combining columns of the same type together in series to increase the pore volume. The oligomers in the low molecular weight region are well resolved up to oligomer P10. The chromatogram of glucose is overlaid as a reference. Using an individual pore column with a specific molecular weight range and of a reduced particle size of 5 micron or even 3 micron, these will lead to high resolution separations. For samples that are polycationic or some strong polyanions, we have SEC columns well suited for these sample types, our Novema Max and MCX columns. For SEC of cationic polymers, the Novema Max packing is an NH functionalized acrylate copolymer, good for samples such as polyethylene amine and those noted here. They are available in both linear and individual pore columns, providing for columns covering wide molecular weight ranges. They are available in particle sizes 5 or 10 micron. These are recommended to run in the operating range of pH 1 to 7 due to the cationic nature of the surface. These columns are also compatible with organic modifiers as may be needed. For the MCX packing, this is a sulfonated styrene divinyl benzene copolymer, suitable for sample types such as polystyrene sulfonate, lignin sulfate, modified starches, and those also mentioned here. These columns are available in 5 individual pore size options with 5 micron and 10 micron particles. This column has a pH range of 1 to 13, though the operating pH range for the samples is suggested to be 7 to 13 due to the anionic nature of the surface. These are also compatible with organic modifiers as well. And also the Novema Max column, this also has select columns available for use with light scattering detectors. Here we show an example of chitosan. Chitosan is a linear polysaccharide bearing amino groups. It's prepared by the conversion of chitin from the shells of crustaceans. Due to its amino group, chitosan is a polycation under acidic eluent conditions. The Novema Max columns are well suited for the SEC analysis of chitosan. Here we have an overlay of 4 different chitosan samples measured with a set of 3 Novema Max ultra-high molecular weight range columns. You can see that we have a nice peak shape and distribution for the 4 polymers being analyzed, and we can easily see the differences between them. We've talked about the GPC SEC product families and the columns we would use for the separation of our polymers, but we also need to talk about and think about guards to protect our analytical columns. We will always recommend using a guard column if there is one available for the column set that you are using. So what do guards do? Guards help to protect the main column set. They help to filter particulates, prevent unwanted chemical contamination, and protect against pressure spikes. What they do not do is they do not replace having good sample cleanup and preparation, nor do they replace proper column hygiene and care. In a lot of the last slides we went through, I mentioned for a lot of the product families, we have columns that are recommended for use with light scattering detectors. Often those working with these detectors will make mention about background or baseline noises and how this can be an issue. This noise can come from both one's mobile phase or it can sometimes comes from the columns. You've probably heard of particle shedding. Users can save themselves a lot of time by using columns that have been specifically prepared for use with light scattering detectors. These columns are manufactured to be made to be LS ready and do not require lengthy flushing prior to use. These columns can be easily identified from their part numbers. The part number will end in LS to indicate they're light scattering ready, or in some column description you will see the term LUX being used, indicating these are also good for use with light scattering detectors. As we've noted, it's very standard practice in GPC and SEC to see columns in series used. When selecting our columns and we're putting our columns together in series, what are we doing this for? Running 2 columns together in series using different pore sizes, When doing this, we're doing this to extend the molecular weight resolving range, which will enable analysis for multiple attributes of our sample in one run. Running two columns in series that are using the same pore size or the same type of column, maybe two of the same mixed or linear columns together. In this case, by adding the second column, we've increased our available pore volume for our separation. Increasing the pore volume will increase resolution. Maybe we choose that we want to use a packing of smaller particle size. This might be because we're looking to increase our resolution but do not want to increase the number of columns we use for our analysis. If using a packing of smaller particle size, decreasing the particle size will increase the efficiency of the column. When combining columns in series, it's very important to be sure that the columns will work well together. The resolving range of an individual pore column can be increased by coupling it in series to another column with a different pore size. The key to successful coupling is that the linear calibrations of the columns must complement each other without too much overlap. In this example, we're combining two 10-micron columns, a 500 angstrom and a 10 to the 4 angstrom. The 500 angstrom column's upper molecular weight limit is 30,000. The upper limit for the 10 to the 4 is 400,000, while its lower limit is 10,000. A little bit of an overlap, but not too much. The slopes of the two columns are also very similar. Putting these two columns together in series now gives an effective calibration range from $500 to $400,000, much wider than either column used on its own. You do need to be careful, though, when working with individual columns and putting them together in series. Shown is an example of how columns can be incorrectly coupled. Again, we show the 500 angstrom pore size, but the other column is a 10-micron 10 to the 6 column. The 500 angstroms linear range is up to 30,000, whereas the 10 to the 6 has a range of 600,000 to 30 million. Trying to put these two columns together would not be advised. As shown here, this leaves a molecular weight range gap from 30,000 to 600,000 between the linear ranges of the two columns. And if we look here at the two calibration slopes, we can see that they are not similar. One is very steep and sharp, and the other is fairly low and flat. Sorry. If using these two columns in series, any polymers which fall into this gap in this area of mismatch, the polymers would not be properly separated, resulted very likely in changes in retention and unusual peak shapes due to this dislocation. In order to have a near linear calibration range from 500 to 10 million, it would be necessary to also couple either a 10 to the 4th or 10 to the 5th column in series in addition to these two. Here's that example now showing the individual pore set with a 10 to the 4th column now added. The calibration slopes now for the set match well, and one can see the full molecular weight range for the set is well covered. Pore size mismatch. It often occurs when there is a sudden change in the slope of the calibration curve. When can it occur? It can occur if there is an incorrect combination of columns from individual pore sizes put together. It can also occur if you use a combination of linear, mixed, or multi-pore columns with a single pore size column. It can also occur if you use a combination of two different linear, mixed, or multi-pore column types together. To avoid this, it's recommended you use recommended combinations of individual pore sizes. You only use linear or mixed or multi-porous columns of the same type together with each other. And if you're unsure, you can consult and use the new GPC SEC column selector tool. And the link for that is provided here. Here's an example showing some PL-gel mixed B columns run both singly and then combined in a set of 3. The mixed B column is a larger 10 micron particle and has a molecular weight range of 500 to 10 million, and here we're running a set of EasyCal PS standards. You can see with running one 10 micron column, we see our 5 standard peaks are resolved, but not very well resolved. With using the mixed columns, as we stated, it's recommended to use columns of the same type together in series, So next we have a series of 3 mixed columns together in series, and we have no mismatch of our columns. We have more pore volume now for our separation, and as a result, we see much improved resolution for our polystyrene standard peaks. When considering the columns to choose for your GPC and SEC analysis, solvent consideration for your column selection is important. Some criteria for solvent selection: it's the factor that principally controls which type of column is selected for GPC analysis is the solvent. Many polymers dissolve in only a limited number of solvents. The columns used must be compatible with the solvent of choice. The solvent of choice must permit adequate detection. You need to have a balanced polarity for the sample type, the solvent, and the column packing. And most importantly, the size exclusion mechanism must be maintained. As we said, most polymers are soluble in a small or limited number of solvents. Here's a table that is listing some common solvents used depending upon what type of sample one might be working with. As we've talked about our column families, when looking at our conditions we might use for our polymers, we must also check to be sure that a solvent will be appropriate for the column we've selected. One could consult the column user guide. We'd also want to be sure that we have balanced polarities for the column packing, solvent, and sample so that the size mechanism is maintained. In addition to the solvent, on occasion one might find that an additive might be needed. Reasons for additives to be employed are these will minimize non-size exclusion interactions that might be happening between the sample and the column, and they can also be used to stabilize the solution of the polymer. If unsure of what might be appropriate for your samples, I've put a reference to the Polymer to Solvents Reference Table technical note here. In it, you can look up your polymer and find information for recommended solvent, column suggestions, plus example, technical, and application notes. A couple tips relating to the use of additives for either organic or aqueous SEC. Addition of salts might be required to aqueous in polar organics. It's the preferred method for eliminating polar interactions through electrostatic screenings. Just remember, salts should be flushed from your system after the analysis. For water-soluble polymers, interactions can also be minimized by the addition of an organic solvent, such as methanol. Loose bases, such as polyamines or polyamides, they may interact with polymeric media, but this can be eliminated by the addition of an amine to the mobile phase, such as triethylamine. Here's an example for an amine-containing sample. Here we have hustavin, which is soluble in THF, but when run on the polystyrene divinyl benzene mixed E column, we don't see very good separation for the sample. And we see a bit of tailing, which is a good indicator of interaction and non-SEC behavior. Because of the amine present in the sample and our packing is TSDVB, we actually need to modify the mobile phase. In this lower chromatogram, you can see that by adding a small amount of TEA to the THF, we have reduced the interactions that may be occurring, and now we have a nice separation for the sample and its oligomers. For our columns, when doing conventional GPC, it's important to calibrate your columns with a set of calibration standards. Much like what we did for our sample, we need to also consider for our polymer standards. Choice of standards will depend on the column you are using and the mobile phase conditions being used. Here we have a table for some standards that are often recommended for the various mobile phase conditions that might be used. What type of polymer standards are available? In Agilent's standard portfolio, there are a number of different formats that you might find. Easy vial or ready calibration kits. These kits are supplied as 10 to 12 different molecular weight standards per kit. There's a known amount of standard supplied. You add a certain volume of solvent to the colored vials for fast and easy preparation for an accurate concentration. You make 3 injections from the vials for a fast and easy 12-point calibration of your column. Easy Cals. This is a kit that is only available for polystyrene standards, and it comes in 2 molecular weight ranges. This is an easy 3-step process to use. You take a spatula that has a polymer film coated on the end of the spatula that contains 5 different molecular weight standards. You put your spatula into a sample vial, add a given amount of solvent, and allow the polymers to come into solution. make 2 injections, and have an easy 10-point calibration. There are also traditional calibration kits as well as individual polymer standards. There are many different standard types available covering all molecular weight ranges. The individual polymer standards are also offered in various quantity options. When sourcing standards, it's critical to try to select the narrowest polydispersity standards possible. If a larger polydispersity standard is used, reproducibility can be compromised as the MP, the peak average molecular weight, will be less defined from injection to injection. Agilent's GPC SEC polymer standards meet these narrow dispersity requirements. The standards are manufactured under an ISO-approved quality system. Each standard is fully traceable with a unique batch number and provided with a complete certificate of analysis. And all certificates of analysis include details of the exact method and characterization results for maximum transparency and reproducibility. Here on the right is an example standard certificate for one of the individual polymer PEO standards. This is an example certificate for one of the polymer standard kits. This is the certificate for an Easy Vial polymer standard kit. In the table provided, the molecular weight information is provided for the 12 individual polymer standards. The mass per vial for each polymer is also given so that an accurate concentration can be prepared. Complete details of the method and characterization results are also provided for each standard. For each colored vial, you could see an example sample chromatogram is depicted in color, showing the separation of the 4 standards. In addition, a full calibration plot is also provided. We often get questions around preparations of the polymer standards and how they should be prepared. When running GPC and SEC, it's recommended that the standard should always be dissolved in the same solvent being used as the mobile phase. Any vortexing, sonicating, and shaking of the standard should also be avoided. All of these high shear activities could inevitably result in a change of peak shape retention time and molecular weight. The concentration of the standard is also of critical importance. Too high a concentration can lead to reduced mass transfer and band broadening due to excessive sample viscosity. Loss of resolution is also a factor. You can see this in the examples to the right. Too low a concentration, and the signal-to-noise ratio will be too small to reproducibly integrate. And also, how frequently should the standards be prepared? Typically, the standards are stable in the form they're supplied in, but once they are made up, they can degrade, expedited by UV and heat. It's typically good practice to make up new standards on a weekly basis. For any questions relating to preparation of standards, one could refer to the user guide for polymer standards. The link is provided here. Another question very often asked regarding the standards is how often should you calibrate? The frequency of calibration is subjective. For continuous work, it's advised to calibrate daily, but with the use of an internal verification, a weekly calibration should be performed at minimum. Once a week is suggested if no major changes occur within the systems or columns. It is essential to recalibrate whenever a component of the system is altered or changed, or if there is an eluent change. Calibrating frequently can also help to identify potential issues and can allow you to quickly put into place corrective or preventative steps in case troubleshooting might be in need. Some quick information for when you get your GPC column. Before using your column, please refer to your column user guide. It contains a lot of helpful information provided here. Here I've shown a couple example user guide examples and have provided the web links for where these user guides can be found. Each column also comes with a column testing report, an example shown here for an aquagel mixed column. When a column is new and you've installed it on your system, it's a good idea to test it at its first use. Do a performance check of your column. Run a checkout standard. Example, run the sample shown in the test chromatogram or another suitable low molecular weight sample. In the case of testing an aquagel column, glycerol is used. Record the difference. Use this as a base value for your column. This is for your column on your system. Perform this again if the column seems to lose performance and compare the results from your first run. In addition, it'd be recommended that you run a set of polymer standards for your column. Maybe it might be one or two standards, or it could be the set you want to use for calibrating your column. But again, this is to set a starting point with a known for your column at its first use. And if you start to suspect that the column is losing performance, run this again and compare. Lastly, I wanted to touch briefly on the topic of column and system consumables. When installing a new column, it's always important to check and to know what type of fittings and ferrules are required for the type of column you'll be using. The result of using improper fittings and ferrules can lead to poor chromatography, broader tailing peaks, or increased dispersion and loss of resolution. This also could result in added maintenance costs. You may see added troubleshooting. You could also have an issue with over-tightening, which could result in column damage. Note also that the distance at the end of the capillary can differ. This can differ between column manufacturers, but this can also be different between different brands from the same manufacturer. Check the compatibility of the two connectors between the column and the instrument. If it's in doubt, use new connectors to connect with the new column. Connectors and the replaced column, those can be stored. To avoid having these issues, one can consider using a quick turn style fitting. Swage ferrule will no longer be an issue. With its spring-loaded design, it provides for a correct connection every time. Plastic connectors or ferrules such as PEEK, just use these with caution. Before using, be sure to check the temperature limits, the pressure ratings, and for these fittings. If we talk about fittings, we must also talk about tubings. It's important to work with tubing that's appropriate for the size column you're working with. This is especially important in the sample flow path. Having tubing that's too wide or too long can contribute to extra column or dead, negatively affect your chromatography. If looking at this example here, we're looking at some polymer standards being run, and we see that the peak shape is between the peaks is not that great either. This is due to using wide bore, larger ID tubing. Looking at the bottom chromatogram, we use a smaller ID narrow bore connecting tubing with an appropriate length. What we now see is improved peak shape, improved peak-to-peak resolution, and increased response for our sample. Here I've listed some of the other most common consumables that you might want to keep on hand when you're doing GPC and SEC. And Agilent also has a great deal of research your GPC SEC application, from information on our web pages to product guides, application references, to column selector tools. And lastly, for my group here at Agilent, the column and chemistries, LC column technical support. This is how you can reach us. US and Canada. Supplied here are our contact phone numbers and email notes. We can also be reached through Agilent chat from most of the Agilent web product pages. And thank you very much for your time today.
Thank you, Jean, for that very informative presentation. I'll go ahead and give everyone some time to input any questions into the Q&A box now. In the meantime, I'll go over a few points. The recording itself will be available in approximately 24 hours along with any additional resources that were mentioned, which will be uploaded to the resource list. Please note this is an ongoing series. You can see the next event listed in the slides currently displayed. So please feel free to join if this topic is of interest to you. And then this is the URL where we post the on-demand recordings. You can check out and register for the upcoming events as well. I'll include this link plus the on-demand link in today's session in the email, and I'll send out sometime tomorrow. So be on the lookout for that in your inbox. Moving on to our Q&A portion, it looks like we have a few questions here. So I will start out with this one. What kind of polymers can you take to do the calibration? If you have a polymer that you only know the composition, can you do the calibration curve with another polymer that knows its MW? What about positive and negative polymers?
I'm kind of looking for that question here in the book. Oh, what kind of polymers can you take to do the if the polymer can you do the calibration with another column? Okay. Well, I mean, what is best if you're trying to do standards, you want to try to pick a polymer that is going to be most like the sample that you are working with. But in a lot, that just might not be the case. There might not be that type of polymer available as a GPC SEC. Conventional GPC, and you're running another type of polymer that might be able to use in the conditions, molecular weights that you're calculating back will be relative to the standards that you're using. That's a very common do things with GPC. If absolute molecular weights are required, you can use something like which would involve multi-detector GPC if you're trying to get molecular weights that are more absolute for the polymer. I hope that answers part of their question.
Perfect. And then this next question, mixed columns and single pour columns be combined in a set.
Say that one again, Michael. Sorry.
Oh, sorry about that. It says and single pour columns be combined in a set.
Can 4 columns be combined in a set?
It says 4 columns be combined in a set with mixed columns.
Oh, it's not recommended. We'll always tell you that if you're working with a mixed bed column, it's best to use a linear column with a linear column. With that, if you look at the calibration plots of these columns, those calibration plots are going to be similar. If you remember back to the slide that I showed that showed combining individual pour columns where the slopes of the columns were different from another, if you tried to combine those 2 columns, you're going to have a mismatch between them. And that's what can happen with combining, say, a linear and a mixed column with an individual pour column. There'll be an area where that initial slope is going to change due to the slope of the individual pour column kicking in. So it's usually at the area where it's the exclusion limit of the individual pour column. If your sample is eluting in and around that area, you potentially could see some false information relating to either, like shouldering or, a bimodal look to your sample. So if you can avoid doing that, I would avoid doing that.
Thank you. The next question is asking, does each column require special standards, or would multi-angle light scattering detection reduce the need for standards?
If people are going to be working with multi-detection and light scattering detectors, they don't necessarily need to, because they will be working with the light scattering detectors. Some people will still their columns, because one of the things that calibration standards can be very helpful for is also if problems with your columns, having some information relating to the calibration of the columns can be very helpful in troubleshooting. It's not necessary if people are doing multi-detection, unless they're doing calibration. Universal calibration will require calibrating the columns.
Next question is asking, refractive index detector more effective for detecting polymers?
Is what?
Is the
detector more effective for detecting polymers?
You were cutting out with saying what type of detector it was.
It says refractive index detector.
Oh, okay, the
So
refractive
RI
index detector?
Yeah.
Okay. It's as most commonly seen and used for GPC SEC. It's 30 plus years that I've been helping to support GPC and SEC columns. It tends to be used. There's a lot of history with it for a lot of polymers. The solvents that they're working in, the refractive index detector, it does show, a lot of the polymers and the different solvents are very good. It's a very good concentration detector, and it is used a lot in GPC SEC work.
Perfect. This question is asking, when performing the column calibration, every analysis.
What about what? I didn't know. When performing the calibration, does it have to be done with every analysis? If you're starting a new application and you've got a new column and you're working with certain and you're doing conventional GPC, yes, it's important to calibrate the column if you're looking to, determine molecular weight average for your sample. If you are continuing to work on that same application, how frequently you might calibrate can vary. We will suggest, maybe running an internal standard on occasion, or calibrating weekly would definitely be recommended. If you were changing anything relating to the analysis, if you were putting another column in series, if you were going to go to a different mobile phase condition, you absolutely would have to recalibrate under those conditions.
Perfect. And this question is asking, what kinds of columns would you recommend for native protein MS?
If we're talking for SEC of proteins, we've got a whole different product line for SEC of proteins. The columns are called Advanced Bio SEC. And those are the ones that we would recommend for protein work. I would not. I wouldn't probably look to either something like the Suprema or the Aquagel that we talked about today. I probably wouldn't look to these because the advanced bios are much more well suited for protein work for that application.
Perfect. And we have time for a few more questions. This one is asking, are guard columns solvent dependent?
Well, the guard will be solvent dependent potentially if you're looking at guards from different product families. So, for example, like with the PL gel guard columns, those will be guard columns used in organics. The Aquagel or the Suprema guard columns are going to be those that are going to be used with aqueous conditions. So you always want to, we would suggest, if you're buying PL gel columns, buy yourself a PL gel guard. If you're using columns, buy yourself a Suprema guard. That would be recommended for the same type of product family. So, within the product family that's the same as your analytical column, that should work.
And the last question here is asking, can you recommend columns and mobile phase for analyzing phenolic?
Phenolics?
Yes.
I think phenolics potentially, depending upon maybe what they are, the molecular weight range of them. I think phenolics might be soluble in THF. There might be others that might be soluble in medium organic solvents like maybe DMF. So depending upon maybe what they found our sample is soluble in, we might look to either maybe the gram columns that are the ones for or potentially something like the PL gel could be considered, but they might need to have a little bit more information on that. But I could follow up with that person. But that's what I'd be thinking for those samples.
Perfect. So at this point, it does appear that we answered most of the submitted questions. If we haven't answered your question, it will be answered at a later date. So I'll proceed with closing the event. So please join me once again in thanking our presenter, Jean Lane, for her fantastic presentation. If you have any additional questions, the Q&A engagement tool will still be available within the on-demand console. Those will be captured and replied to at a later date. You can also reach out to Jean directly via email. Her email is listed in the speaker bio engagement tool on your platform, so please feel free to utilize that if you'd like to send her a direct mail. Thank you all once again for attending today's event, and on behalf of Agilent Technologies, we wish you a good day.